Hello and welcome back. Today we're going to be talking about the image of a function. As we defined before, if f is a function with domain x and codomain y, and we have an element little x in big X, the image of little x is f of x. The image of an element is always an element of the codomain. We're going to expand the idea of the image of an element to the image of a set. If A is a subset of the domain, the image of this set A, we write that as f of capital A. F of A is equal to the set of all f of little a for A in big A. Or in words, it's the set of all elements in Y that are the image of some element of the set capital A. A key distinction here is that the image of a set A is a set itself. It's a subset of the codomain. To compute the image of an element, we evaluate the function at that element. We might have a closed formula. For example, f of x is equal to 3x. In that case, this is what we're used to. F of 6 is 3 times 6, which is equal to 18. When you have an arrow diagram, we look to see where does the arrow go? The arrow from C goes to D, and so f of C is equal to D. In two-line notation, the inputs are in the top row and the outputs are in the bottom row, and so if we want to calculate f of 2, we look below the element 2 and we see the element 3 in the codomain. And then if we have a graph, for example f of 1, we look at where 1 is in the domain and we see what is the y value of the function at 1, we get 6. If instead we're computing the image of a set, we need to evaluate the function at every element of capital A and collect them in a set. If we have f of 1, 2, 4, when we're given f here in two-line notation, then what we need to do is we need to see what are the function values of 1, 2, and 4, and we put them in a set. And so f of 1, 2, 4 is the set containing a smiley face and an ambivalent face. In more complicated situations, you may need to understand more deeply the set or the function and any patterns involved. Here is an example. Let capital P be the set of prime numbers, and let capital Q be the prime numbers greater than or equal to 10. So that's a subset of the set of all prime numbers. For any p in capital P, define f of p to be equal to p mod 10. So we take the remainder after we divide by 10. Determine f of q. What are all possible function values when you plug in values of q? First, understand what the set q is. So the set p starts out 2, 3, 5, 7, but then q is everything greater than or equal to 10. So 11, 13, 17, 19, 23, 29, etc. When we take these values mod 10, what we get is 1 mod 10, 3 mod 10, 7 mod 10, 9 mod 10, 3 mod 10, 9 mod 10. We seem to get odd numbers, except 5. Could that possibly be the answer? Prime numbers are numbers that are only divisible by themselves and 1. Any even number bigger than 2 is therefore not prime because 2 divides it. The possible outputs are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And what we're recognizing is that we can't have any even numbers. And could we possibly have a 5? If we have 15 or 25 or 35, all of those numbers are divisible by 5. That means 5 cannot possibly appear as a value in f of q, and since all of the other numbers do appear, then f of q is equal to 1, 3, 7, and 9. Let's talk about a few special cases of calculating the image. As a reminder, here's the definition of f of capital A. So let's say we wanted to figure out what f of the empty set is. What are the elements in the empty set? There's no elements. What is f of every element in the set? There's no elements to calculate. And so f of the empty set is the empty set. What about f of the whole domain? Well, we have all elements are in capital X. What is f of capital X? It's the set of all possible values that you can get, which is the range of the function. All right, that's it for this video. See you soon.